Buenos dias, everyone. Mucho gusto. I do want to say thank you for having me for this presentation. I hope you guys like it. It's going to be a lot about a lot of the processes that we do at Theory 6 for kickoff and everything in terms of how we decide what to do with our robot. So I'm just going to share my presentation and then we can go from there. Okay, so the way it's going to work is just a little bit about myself to start off with. I'm a graduate from University of Waterloo, where I studied Bachelor of Applied Science in Mechanical Engineering. And I actually joined FRC quite a bit of time ago. It was in 2007, and I was a student for 2 years, and then I've been a mentor ever since for Team 1241. Now at our school, we actually have 2 teams, 1241 and 1285. So we actually run a dual team system, which is kind of cool. That's to engage a lot of people into our program. And I'm the lead engineering mentor for FRC 1241. Now in my day job, I actually work at a company called Gypsum Technologies, and I am a mechanical engineer there. So that's a little bit about me, and I'll go over what we're going to see today. So I'm going to go over a little bit about kickoff and what to expect, a little bit about strategic mechanism selection. So I'm going to present you guys with different options as to the different mechanisms out there for different subsystems. And then I will also provide you with tips for designing, some design success stories, and then some common suppliers and references that we use at FRC. So Team 1241 is actually a team from Canada in Ontario. And we're one of the top teams here in Canada, which is kind of good. And we've been up and coming. We've had a lot of success in the past few years, including winning the World Championships in 2013. So it's been a lot of success, but we've learned from a lot of the top teams around the world. And some of those ideas I wanted to share with you today. So the importance of kickoff weekend. There are certain decisions that our team and a lot of top teams make during the first 2 days of kickoff. So the Saturday, you receive your game and the animation and all the rules and everything like that. And then you also have Sunday of that day. Some of the major decisions that we make during kickoff are the drive chassis. So what type of chassis we're going to be using. Strategic capabilities. So pretty much what your robot can do and what we choose not to do. And then the mechanisms that we want to prototype. So our team actually does a lot of prototyping, but most of the time we make it out of wood, and we only power the mechanisms that we think need more testing. So on the image that you see on the right-hand side, you'll see this is from 2018, where we prototyped our robot. And as you can tell, we made a wood mock-up of almost everything on there. But the drivetrain that you see on the floor is not powered. We just like push it around with our hands. And then there's also the intake that is powered because we wanted to see how it reacts with the cube. So we try our best to prototype as much as possible for only things that we need to test. So kickoff schedules and some of the design takeaways that we do and thing. What we do is we discuss all possible movements and functions which you need, and this will be on the Saturday. So everything that the robot can possibly do, and we also decide what we want our robot to do. So this is where we get the most creative. We try to make sure that all the team members are involved so that they could outline everything that you can do inside an FRC game. This also transfers to FTC, where you want to get all the ideas on the table. So then you can pick and choose what you want to do. And then on Sunday, we actually discuss the 4 major systems, which is the intake, the tool, the endgame, and the drive chassis. And what we do is we essentially brainstorm ideas and mechanisms that would be able to achieve what we decided on Saturday. So if we know that the robot has to pick up a gear from the floor, or it has to pick up balls from the floor, or it has to shoot balls into the high goal or something like that, then we want to make sure that anything that we propose on the Sunday in terms of mechanisms is capable of doing that. So drivetrain should always be selected by this point. For us, we prefer the West Coast drivetrain just because it's the simplest for us and we've been used to it and we've been perfecting it for the past few years. But then I'll show you guys some of the more new drivetrains that have come up and are becoming more popular now instead of just tank drive and everything like that. So you'll see those today. The other thing that we do is we set prototype variables for each proof of concept. So what we want to do is if we have two prototypes for a scoring mechanism that are equal that you could have designed. So let's say it's the game in 2016 where you had to shoot the boulders into the castle. If you had a catapult versus a wheeled shooter, what prototypes would you build and what variables would you test so that you pick one over the other? So in this case, you could do like accuracy, you could do distance of shot, you can do speed variables that you have to adjust so that you can get the accuracy that you want, those kind of things. And then the last one, lead mentors and key lead students, then we'll do preliminary geometric studies. So what we do is we do 2D drawings on Inventor, we use Autodesk Inventor, and then we try to manipulate it so that when we create our prototypes in the following week, we're able to use geometry that actually does work rather than just putting everything together by hand. So a lot of our prototypes are very intentional and it's to adjust variables and distances and pinch and roller heights and everything like that so that the prototype works. And we also start our drivetrain design. So I know a lot of this can be really quick and it's the first weekend. You might want to know more about the game and you might want to read the rules a bit more. So some top teams actually, they create a quiz. So if you read the manual on Saturday and complete the quiz, then only you can come on to Sunday to be part of the discussion. That's one way of going about it. Some teams, like top teams, like even OP 2056, they take the Sunday off, I believe. So they don't actually meet up on the Sunday so that the team has a break, they can read all they want, and then most of their discussion happens on Monday. So try to find out what works for your team at best. We like to be ahead of the game and try to finish a lot of it on that first weekend so that during the week, we're just focusing on prototyping and try to making sure that the robot functions work together and all the subsystems work together. So movements and preferences. This is what happens on Saturday when we actually list all possible robot movements. What we like to do is make sure that everything is covered. There's nothing off the table in terms of the things that a robot can do. So we try to make sure that all of it is there. The other thing we also do is try to determine robot roles and which one you prefer. So we've been doing this a little bit more recently because what you can do is you can pick what we like to call is like types of robots that you'll see on the field. So in this case, the chart that you see on the right-hand side is actually from 2017. So that's when you had gears, you had balls, and you had a hang. Those were the three major functionalities that your robot would want to do during the. So we had the pros and cons for each of the different types of robots where you would be a gear and a hang robot, a ball and a hang robot, or a ball and a gear and a hang robot. And you'll see all those variances and how it lays out. And then we try to create that sort of archetype or that sort of robot eventually once we pick it. So the other thing is also outline specific benchmarks for being successful in that role. So if you pick one of the roles, no matter what it is, you want to try to be the best at it. So if you're going to be the gear hang robot, you better be the fastest gear scoring robot that would be there. And that allows you to be very strategic and be able to be seen as a good first pick. Or actually, if you choose one of these niche roles properly, you could actually rank first or rank really high to be able to pick your alliance as well. So you have to be really careful in terms of what you pick here. But if you do choose it, you want to optimize it to be the best in that category so that you're seen as a good first pick. Now, what we do is also categorize all our robot movements into needs and wants. So needs are absolutely necessary. The robot has to achieve that in its functionality. But then wants are planned to be integrated into design. So you could keep them in there, but if there's a chance that it doesn't happen, that's okay. So sometimes it could be like, maybe if you wanted to shoot 5 balls in autonomous and that was a want, but your need is 3 balls in autonomous, right? You can choose that. And then if you get 4, if you get 5, that's great. But if you get 3, then you've achieved your goal and that's good too. So now here's the robot example from 2017 again. So as you can tell, we actually listed out the pros and cons of each of the different types of roles. These are not the list of movements. This is just the types of roles and what our team preferred. And then what we would do is we would try to make sure that you have enough representation from your students and stuff like that. This was just in process. So we had 17 votes and we kind of like carried it out. But then what we do on 1241 is to get a consensus. So these 6 people that are in gear hang, or these 11 people in ball gear hang, have to talk to each other and make sure that everyone is agreeing on the same role. So sometimes maybe we don't want to do ball gear hang and then we move to gear hang, or the same thing before. Like you need all 17 people that are in here to be in one category so that everybody's on board and everybody agrees with your robot. And this is really important in the future because when you're working on your robot for 6 weeks, 8 weeks, going to competition and things like that, you don't want anybody to feel left out or feel like they didn't get a chance to voice their opinions and then the decision made wasn't what they wanted. Because as a team, you should be working as a team too. So it just allows everyone to feel more proud of what they put onto the field if everybody is in agreement that that is what they want to do. So here are some of the movements and preferences we do on the first day. So this is from 2019, and this is how we determine some of the movements that take place during a match. So as you can see, there's quite a lot of movements that a robot would do during that session. I'm just going to double check that my audio is also there. So I'm just going to stop sharing for a quick second just to make sure. And then I'll just share it again. Okay, this is better. Let's go on there. So movements and preferences. One of the things we also like to do is separate the autonomous movements and preferences and the endgame movements and preferences, because these two can sometimes be their own unique mechanisms that you can have just for autonomous or just for endgame. So for example, in 2013, we had 254's level 3 climb, where it climbed the pyramid. In 2019, there were a lot of teams that used the suction cup method in order to climb to level 3. And then in 2017, we had a little tiny like claw mechanism that held the gear during autonomous, so it was easier to score the gear. So let me just show you some of that. So here's 254 from 2013. So you can see it here.
Started from the bottom, now we're here. Started from the bottom, now.
So that's a really crazy robot, a really complicated robot. But you see here that they actually chose a very good level 3 climb that they've designed, but it looks simple. A lot of it is very, very complicated. And I'll show you some pictures later as to like why it's so complicated. But the idea was that they sacrificed some of their other components in order to be able to do this as their level 3 climb. So 254 that year was not able to pick up discs from the human feeder station. They had to pick it up from the floor. So that is one thing that they gave up so that they could have this climb. This meant that the human player had to put discs onto the floor, and then 254 had to pick up one at a time. So at the feeder station, they were really slow. They also had to make sure that their shooter is very narrow. So they could only like have discs in one line. So they had to really do a lot of mechanisms to try to make sure it shoots the ball or shoots the disc, however, and it was kind of slow. So just in case you have to wonder that like if teams do it all and they're really fast at it and everything like that, sometimes you do have to sacrifice the quality of other mechanisms in order to achieve something that you really wanted, which in this case was the fastest level 3 climb.
Whole team here.
This was a video for the suction cup. So here's just a little preview. So there were a lot of teams that did this one, and they sacrificed a lot of space in order to make it happen. So this allowed other robots to get onto level 3 with them. It took away some of the space that a robot would take up on that top platform. And it was a really great system. And a lot of teams were able to implement it and use it. And it was a great way to actually figure out there. But this is a dedicated mechanism that was implemented so that people would do it as part of the end game. And so there were a few teams that implemented it at Worlds. You can see that Poofs didn't have this mechanism during their regionals, but they were able to implement it at Worlds in order to reach a higher level for their robot. And on the simpler side, this is what I was talking about as the auto gear holder. So this was a little mechanism that was right there at the back of our robot, and it allowed the gears to be really high up. So our human player actually took the peg and raised it up so that he could target any of these ribs, and it was completely exposed. And it shortened the amount of time that is needed for dropping off that gear to the human player. So sometimes a simple mechanism like that can give you the advantage, and you could start either shooting balls really quickly in this case, or you could start your gear cycles early too. So those kind of little things watch out for, because they will help you reach a higher level. So now, when you do a strategic mechanism selection, most robots can be broken down into 4 main subsystems, which is the drivetrain, the intake, the tool, and the endgame. So drivetrain is responsible for just moving the robot around on the field through any obstacles or defense. The intake is to get the game piece into your robot. The tool is mainly for scoring or making sure that the robot can manipulate the game piece and put it anywhere it wants to. And then the last is the end game, which is during the final portion of the game, depending on if the game has an end game or not. So here are some of the drivetrains that you could pick when you're doing this year's game or future games. This is the one that we most prefer. It's the most easy one in our opinion in terms of picking. There's only 2 driven sides. It's simple for programming. You have a right side and a left side, and then you have wheels on either side that are powered with individual gearboxes. It uses high traction wheels so that it can push other robots and everything like that easy. It's easy to go forward and back, but sometimes it can be hard to turn. So you just have to be careful of that. The difficulty for this one is easy-ish. Nothing in FRC is really easy, but at least this is one of the easiest ones you can go for. So the next one is Holonomic Drive. So it includes independent driven wheels, but all of them have some sort of wheels that are at different angles. And they have these rollers so that it could kind of like glide into different positions. The one up top is an H drive is how we call it. So there are wheels and there are wheels perpendicular to that are all driven so that the robot can go side to side. It is somewhat complex. There's a lot of moving parts and a lot of different axes that everything is in, but this one is bad for pushing. So with this robot, a lot of defense can be played on it. Like you can move around the other robots, but you have to be careful that if you're trying to play defense with this, it's really easy to push. This one difficulty would be harder than the first one, for sure. But you can move sideways, which is kind of cool. And it allows you to have a whole bunch of different types of autonomouses or movements during the gameplay. The next one, which is the most complicated, is the Swerve Drive. And this is getting more and more popular now because drivers are getting more and more faster, and there's a lot more technology that is made in terms of the gyros and encoders and things like that. So this one, each corner has its own separate axes. So you can think of it as like a trolley or a cart at the shopping center. And each of them are driven and can rotate, uses high traction wheels so it could push against defense as well. But it can also move around in any direction that you want. So it's very difficult to program. A lot of models and kinematic equations and stuff have to be used for it. And especially if you wanted to make it field oriented so that it would know its orientation at all times, it is very difficult to program this. But if your team chooses to do it, the rewards are actually really great too, because you can go around defense. So this mechanism or this type of drivetrain, the Swerve drivetrain, is not needed all the time, but if you do it well, you can have a lot of reward. But if you do it badly, then it can cause a lot of headache and a lot of problems because there's so many parts that could break or go wrong. Now we're going to move on to intake. One of the biggest principles that we have for intake mechanisms is touch and go. What that means is that whenever a driver or our robot comes near the game piece and it's able to touch it, you should always have powered surfaces. So what that means is most of the time we will always use rollers or wheels on our intake because you want the game piece to come into your robot. You don't want to be able to like clamp and like have some sort of mechanism that your driver has to be in charge of in order to get the game piece. Just keep in mind that if you have this, then it saves time for your driver. They just have to come near the game piece and it possesses the game piece. So it's really important to have this touch and go feature. This is where most of the time is lost for a lot of drivers, is to just grab a game piece. And you want to make sure that your linear intake speed is always faster than your drive speed. This way, no matter which direction you're moving in, the intake will always able to bring the ball, or in this case, the cube, into your robot. Apply some pressure. You can actually use elastic or pneumatic methods to clamp anything secure if you feel like sometimes it could be too loose or something like that. And then you want to make sure that there's some sort of articulation so it can move or expand and stuff like that for anything that is not round. Generally speaking, when you have a round surface or a round object, your intake doesn't have to be moved. It just needs to be positioned at a proper height. But when you have non-round objects, it does need to flex in order to get possession of the game piece. Now we're going to go into some of the shooter mechanisms that would be there. So for example, first one is the catapult or the elastic launcher. It stores the most amount of potential energy, which means it can actually shoot the farthest, but it needs to be reset after each shot. Sometimes it has a slow fire rate, and the difficulty for this one is medium. I'll show you a catapult that Robo Wranglers made in 2014. And then they also made a catapult here, which was pneumatic driven in 2016. So you can see there that it was just retracting back and then it's shooting forward. There are lots of elastic bands on this side in order to be able to actually shoot the robot and the ball. So the next one is the Flywheel Shooter. This one is good for rapid or high volume shooting, and you can try to be actually pretty consistent. The hardest part about this is you need time to tune it and to program it, because you want to make sure that the wheel is spinning exactly the same way for every ball that it's shooting or every game object that it's shooting. So although it has a high fire rate, like it can shoot a lot of objects at once, you do want to make sure that it is programmed, it has encoders and everything like that, so that you're able to actually take advantage of how fast it can shoot. So there's just 118 from 2017. They have some of the best flywheel shooters ever. 254 also has really great shooters and stuff. Okay, the next one is the piston or the pneumatic launcher. Essentially, you can just think of it as punching the game piece. Usually it's the least efficient. It has a low range. And then sometimes it doesn't get affected by ball variation, which is kind of good. So it can get consistent because it's independent. It can be pretty compact. And sometimes it's able to be used for different game pieces. So this is kind of cool. The piston and pneumatic launcher is essentially punching the object. It's some of the simplest ones that you can use in order to score a game piece. So now here's probably the most advanced shooter mechanism, which is the turret. It's usually paired up with the flywheel. Sometimes it could be paired up with a catapult. It could be paired up with the pneumatic shooter. But this adds another complexity to your design. So a turret mechanism is able to move independently from your drivetrain so that the scoring mechanism can rotate. In 2019, a lot of teams, or a few teams, used their elevator mechanism on a turret, which was really crazy. I know we discussed it at the first few days of our season in 2019, and we chose not to do it because it was just too complex. But the best way to kind of summarize this one is that it's really difficult. There are a lot of moving parts. There's a lot of points of failure, but you can actually be really beneficial if you use it and you've been able to tune it well. It usually is accompanied with vision tracking, so that as you move the turret, it can auto lock onto whatever it needs to score to. This is good because then your driver doesn't have a lot of things on their plate, and the tool operator doesn't have to press a lot of buttons in order to do this as well. So usually pair it up with vision tracking. And then also we found that if you have a camera that's using vision tracking and stuff like that, sometimes you could add a dampener, like a little piece of rubber or something like that, so that it's not shaking, depending on how you've built your mechanism. So keep that in mind, because your vision tracking is really important. So if the camera is not shaking, then it can properly target. And it requires a large amount of testing. It requires a large amount of programming and things like that. So keep in mind that if you do choose to use the turret or vision tracking, set aside a lot of programming time because you will need it for making it really good. Now I'm going to go over some of the lift mechanisms. There's a few different kinds. There's single jointed arms. There's some elevators and things like that. I'll show you guys some of the key tips for that. So single jointed arms are possibly some of the simplest ones. You essentially just rotate a lever and it will get you to the positions there. Now, keep in mind that you do want to make sure that the longer your arm it is, the more counterbalance or some sort of torque calculation is done so that you can lift it, because the longer the arm, the heavier things can get, and the further away it is from the pivot point, the harder it is for the mechanism to work. Then you have some bar linkages. So there's some that are called the 4-bar linkage, which is this one here. There's some that are actually locking mechanisms that could be used. So this is also a single bar linkage, but it has this 4-bar in order to lock it into place. This allows you to control the angle, and through geometry, you can actually use it so that your object can stay leveled or it can be at a different path. And it allows you to have some sort of simplicity so your driver doesn't have to actually rotate the object in there. The difficulty for this is medium. I mean, you do have extra parts that are moving and things like that, but this is one of the nicest ways to keep the object like in the same orientation, whether it's on the floor or whether it's up on the ground. The next one is the elevator. This is complicated. I do want to say that elevators are actually really difficult because there's a lot of little parts and a lot of little details that allow you to have an elevator that is fast moving up and down, but also durable, because elevators, anytime there's some sort of impact and anytime it runs into something, it can actually bend the elevator out of shape. So you want to keep in mind that even though it's just moving up and down, there's a lot of different things that you need to account for. It is pretty compact. It uses the least amount of space. And also there's a lot of bearings and things that are involved in order to keep it from moving around or falling apart. Sometimes you can create really strong elevators, like the Hot Team 67 was able to create an elevator where it was able to break the scale in 2018 as it was coming down. So there's a lot of good features in an elevator, but it is actually pretty difficult to perfect. And this is perhaps the most complicated one, which is telescopic arms, which is where the actual mechanism collapses within itself. It requires a lot of detail. There is a lot of stages that fit into each other, and you have to make sure you prevent them from twisting in any way and also like rotating them amongst inside. So it's really hard to actually power it too, because you have to get into different little tiny nooks and crannies in order to make it go up and down. So keep that in mind, that this is very difficult, but it is one of the coolest mechanisms that you can go up for. The one image that's on the left side over here, that's 254's telescopic arm from 2013, the one that could climb in 6.42 seconds. It was actually really complicated in how they had to assemble it together. They had their drivetrain power those arms as well, which is really, really complicated too, where you have a power takeoff. So keep this in mind. If you choose to do the telescopic arm, it's actually really difficult too. And the last one is the hanger or the climber. This is good for using a winch system so that it locks into place. It essentially is a pulley or a drum. And then sometimes you have piston or pneumatic hanging mechanisms where all they do is like a piston actuates and brings you back up. So this is something that I wanted you to know as you go through your different design challenges. There's no right answer in an FRC game. As you can tell, I showed you guys a ton of robots, a ton of different mechanisms and stuff like that, but a lot of them were successful. So whatever your team chooses to do, just make sure that you guys optimize it. Try to take advantage of all the time that you have during an FRC to tweak it, make it better, and making sure that it's the best mechanism that you guys can design, no matter what team you're on. Keep things simple. Try to avoid any complicated things that you can see from other robots and other teams, because sometimes they may have a lot more experience with that. We tried our first telescopic arm in 2020 season, and it was a disaster, right? Like it was breaking often. We were breaking parts, and it was actually twisting and things like that. So sometimes doing it for the first time, although we have a lot of lessons learned, if we kept it a little bit more simple, we might have been more successful with that. Pay attention to the orientation of the game piece. So sometimes the orientation that the game piece will be on the floor is different for when you have to score it. In a situation of a ball, that's not the case. But if you have to score like a tube or something like that, keep that in mind, that maybe you can simplify your motions because you just need the orientations. Possess the game piece quickly. Remember to touch and go for any of the game pieces, because that will allow your driver to have an easier time on the field, because FRCT field is really big. There are times where a driver can't see what he's trying to possess in terms of the game piece. So it's best to have a touch and go system. Try to take the load off of the motors when using arms. So try to use some springs or some sort of gas struts or any sort of mechanism to make sure that your motor is not loaded when you're using arms. And use sensors wherever possible. And choose these early so that you know that your programming team can get ahead and start building their code before the robot's even built. So this way it allows you to make sure that everybody's on the same page and they know what to expect. Prove your designs through prototyping, not assumptions. This is something that can be debatable. There's some teams that don't prototype. Our team does prototype and we learn a lot from it. So it's up to you to choose whether you want to prototype or not. But for us, it allows us to see the robot kind of fit into place before we start turning into metal. And pay attention to your skill level and your team's resources. This is a very valuable thing. If you choose to go outside of the box and stuff like that, keep in mind that there are capabilities that teams have that other teams don't. So you just have to make sure that you can understand with your skill level and try to learn as best you can. But if you want to improve your team, you may have to go outside your team's skill level and try something new. This is something that I strongly encourage you to do or try if you have the resources to do it. 1241, like we try to push the limit in terms of what we do, but when you try to reach for higher goals, you can also be unsuccessful or fail and you reach a lower goal. So in 2015, we decided to do twin robots for one of our teams, 1285, and we tried to do a double stacker for 1241. And that was very complicated, very ambitious and things like that. So even top teams like us, when we try, we might be failing to do so. But we learned a lot from it. And then our 2016 season was one of the most successful we've ever had, because we took those practices that we learned from and then we implemented it the year after. So keep that in mind. If you do want to improve your team, you will have to push the boundaries and try to be outside of it in order to kind of raise the skill level inside your team. So now I'm just going to spend a couple minutes on some of the winning designs in the past. So in 2014, Choosy Poofs had a 3-ball hot autonomous. It was really cool to see 2 different intakes and things like that come out to do it. There were also multiple shots that they chose, and multiple hot high goals was actually a really important feature in that. So here's team 33. They were able to shoot from far and then score their balls too. In 2016, the outer work shot, which is the one from the defenses, was really important. That would be really cool because the robots can't touch you or defend you while shooting. We did a lot of ball stealing during there. So we actually sat beside the castle and we were able to score 14 shots in one of the games that we played, which was really cool. And then sometimes teams would do a hanging shot. So they would be able to raise up all the way and shoot the last little ball. And that actually could be a difference because that was 5 points that you could score while hanging that the other team couldn't. So it could be the difference between a win and a loss. I won't show this video right now because I know we're running a little bit out of time. I can come back to it if we choose to, but I'll go over to the 2017. There was a 4-rotor offense where you score all the gears and then you just start playing defense. So then it makes sure that your alliance is able to get the 4 rotors, but your opponents are not. That was kind of a cool one. The hopper autonomous, where the team would go in autonomous to the hopper and get all the balls and then start shooting it. That was really cool because you have triple the value in terms of your scoring. So you could get your 40 RP really easily and the bonus point. In 2018, cube scoring on a moving or a losing scale was really important. So there were a lot of teams that just couldn't reach high enough. And that was a big deal because if you weren't winning your scale and you were stacking cubes, that could actually be a huge setback too. And the last one is just the value of ownership. 3-4 cubes scored in autonomous was really important too. These are some of our common suppliers. This is actually the last slide in my presentation. And these are some of the ones that we use in Canada. Hopefully they're available wherever you are too. And if you do want to know all about everything that we go through, we do release our playbook, which includes all the information that I included today and our entire schedule for the build season. So you could actually check every day of what you need to do. And we've been doing that for the past 3 years. There's the link below too. And hopefully you get this presentation after. And thank you guys for coming. That's really it for me. You can note down my email address too. If you have more questions, I'll be happy to answer them too.
That would be great, Malavya. Thank you very much. I may stay with there's no right answer in FRC. There's not only one right answer while designing and playing in FRC, but of course, all the teams here today will, well, what you just told us and what we will learn from this, it's just amazing. So if we may, now Q&A is open, guys, everybody. So get yourself ready, send your questions, and I'll read them out to Malavya. Oh, so the first question is here, Malavya. So
okay.
From Ricardo, our team is very limited in engineering-related matters. What would you recommend us to make to create a competitive robot?
Okay, so there are a couple of things that you can do. One is try to reach out to any of the top teams that are in your area for engineering support. I know a lot of teams in Canada, we learn from each other. So we always try to bounce ideas off of each other and we create the system where you can access any mentor. The other thing to do is try to do research. A lot of what I learned was because of my research for things that were done in the past. So I try to find a lot of photos. I try to find a lot of top teams, ask a lot of questions to those top teams about how they did what they did in that year. And teams are generally very happy to answer that. FRC is actually, or FIRST in general, is really good because everybody's collaborative. So try to ask questions, try to ask top teams, and try to ask engineers in your area too.
Awesome. So next question comes from Hector Pedraza. Saludos a Monterrey. How is your team going to lead with the robot planning and building with this pandemic situation?
Yeah, that's a good question. For ours, I think a lot of everything that we've been doing has been online. So we've actually held a few mock kickoffs for some of our new students and recruiting them. Unfortunately, our school is not available right now because we're under a lockdown and things like that. But as it opens up, what we like to do is try to teach in person. But if not, then we've been holding a lot of online workshops. To be competitive, I think even for us, we would be reusing a lot of our resources. So we wouldn't be trying to build an entire new robot. I know we had plans for that in the summertime when we had discussed it with our team. But as this is moving along, you kind of have to adapt to it. So we chose not to do that anymore, and we might be able to reuse our robot.
Well, adapting, that's the key word.
Yeah.
So, well, while we get more questions, Malavya, I don't know if you could share with us your email, so in case anyone needs more assistance.
Yeah. Should I put that in the chat? I can do that too.
Yeah, that would be great. So, there you have it. Thank you very much, Malavya. Yeah. So, well, I don't know if you could tell us a bit. What are the plans for your team this season? Anything you're supposing to premiere?
Yeah, so I think we're taking it a little bit slow. A lot of our students are doing more online learning, and we focused a lot more on outreach. So we've been actually hosting a lot of online workshops for different places, doing FLL coaching online as well. But in terms of the FRC season, we're just trying to learn as much as we can. Since the season is a little bit unexpected, like we don't know if tournaments will be happening anytime soon in Canada, at least. We're going to be doing more of a learning experience. So a lot of it is based online. Yeah.
Awesome. So, well, we're getting more questions right now. Arjun Bethia. Are these recordings going to be posted somewhere? We're working on it, Arjun. We'll let you know. Gabriel Lopez, can you put the link to a robot's playbook again?
Yes, I can. Let me do that. And you can also visit our website, theory6.ca, and you should be able to actually see it there too. But let me just copy the link as well so you guys can have it. Are there any other questions, Ricardo?
Well, it looks like we're all done.
Okay, that's good.
Yeah, I think we're gonna set it here. So, Malavya, again, thank you very much for being here. It's been a pleasure to meet you, and we wish you the best of lucks for this upcoming season.
Yeah, thank you for having me. This is a great event, so I hope you guys have a lot of fun later today. And if you have any questions, like I said, feel free to message me. Feel free to email me. I'm happy to answer them for sure.
We're only one email away.
That's exactly right.
Thank you very much, Malavya. Oh,
all right. Thank you, guys. Yeah.
Have a nice day. See you soon.
See you.